Okay, in this lesson we're looking at Unit 2, Chapter 1, Function Transformations, where we're looking at the inverse of a relation, Part 1. Okay, the focus for this lesson is going to be on sketching the graph of the inverse of a relation, determining if a relation and its inverse are functions, and also determining the equation of an inverse. Let's start with the vertical line test for a function. You should have learned in level 1 actually that a graph represents a function when no 2 points on the graph line the same vertical line. If you place a ruler vertically on a graph, then slide it across the graph, if one edge of the ruler intersects the graph in no more than one place, the graph represents a function. It simply means here that if you draw a vertical line, and if the vertical line intersects the graph in more than one point, the graph is not a function. So for example, if we were to look at the 4 examples you see here, I can draw as many vertical lines as I wish on this graph. There will be no vertical line that will intersect the graph in more than one point. So this function, or this graph, does represent a function. So this is a function. The second graph here, again, I can draw as many vertical lines as I wish, and it will always intersect the graph at only one point. It doesn't matter where I draw the vertical line, so this as well is a function. For the third graph, I can draw a vertical line right here that will intersect the graph in more than one place. Because of that, we say that this is not a function. And the same is true with the last graph. If I were to draw a line down through here, it intersects the graph in more than one place, so this again is not a function. It's called the vertical line test for a function. Okay, let's move on to an example here. What we're going to do is we're going to sketch the graph of the inverse of a function, and we're going to use the vertical line test, I guess, to help us determine whether it's a function and whether or not the inverse is a function. So let's do that. Let's start out with this linear function, the f of x equals 1/4 x subtract 5. Let's simply plug in values of x, find values of y, and let's sketch the graph. So we have the we have the x coordinate of the function to be -8. If x is -8, let's plug it in very quickly. -8 times 1/4 is -2. -2 subtract 5 is a -7. If we plug in -4, I'll get -1. -1 subtract 5 is a -6. If I plug in 0, I'll get -5. If I plug in 4, I'll get -4. And if I plug in 8, I'll get -3. So there's a set of points on the original function. Let's quickly plot these here. -8 and -7. We have -4 and -6. We have 0 and -5. We've got 4 and -4. And we've got 8 and -3. And as expected, it's a line, so let's join up these points and let's see what the graph looks like. Graph passes through these points right here, and here is the graph of the original function, the f of x. Okay, let's graph its inverse. Now, the quickest way to graph the inverse function is simply switch the x and y coordinates of the point. Let's do that. -7, -8, -6, -4, -5, 0, -4, 4, -3, and 8. Once I switch the points for x and y, I've now created a points that represent the graph. The points when graph will represent the inverse function. Let's plot these new set of points. I'll do these with a different color. Let's do it. -7 and -8. We have -6 and -4. We got -5 and 0. We got -4 and 4. We got -3 and 8. Let's join up these points and let's see what they look like. And there's the graph of the inverse function we represent that as f to the minus 1 of x to represent the inverse function. What's significantly important here is that this statement right here, look, note that the graphs of the function and its inverse are reflections of each other in the line y equals x. This graph and this graph are reflections of each other in the line y equals x. That will always be the case for a function and its inverse. They will always be reflections of each other in the line y equals x. If I want to find the equation of the inverse, I simply switch x and y and I solve for y. And note I switch x and y because that's exactly what I did in my table of values. I switched x and y. So let's find the equation of the inverse. So the original function is y equals 1/4 x subtract 5. So let's switch x and y. I'll have x equals 1/4 y subtract 5. That's switching x and y. Now let's solve that for y. I get x plus 5 equals 1/4 y. Multiplying through by 4, I will get 4x plus 20 equals y. There's the equation of my inverse function, and I write it like this. F to the minus 1 of x equals 4x plus 20. There's the equation of the inverse function. And that's the graph that you see right here in green. Note the way I represent it again. F to the minus 1 of x represents the inverse function. I found it again by switching x and y and solving for y. That will always give me the equation of the inverse. Okay, let's answer these couple of questions here quickly. Does the graph of the f of x represent a function? Here's the original function, f of x. Does that represent a function? Yes, based on our definition of the vertical line test, it certainly does. Does the inverse represent a function? Yes, it does. I can draw vertical lines as many as I like, and they will only intersect that graph in exactly one place. The domain and range for both of these functions, by the way, are all real numbers. X such that x is numbered in real numbers for the original function, and the range is y such that y is numbered in real numbers. Same is true for the inverse function. X such that x is numbered in real numbers, and the range is y such that y is numbered of the real numbers as well. Okay, so the important things here, if we want to sketch the graph of the inverse function, if I know a set of points in the original function, I simply switch them around. If I want to find the equation of the inverse function, I switch x and y and I solve for y. And of course, very important here, the graph of a function and its inverse are reflections of each other in the line y equals x. Horizontal line test is simply a test used to determine if the graph of an inverse will be a function. If it is possible for a horizontal line to intersect the graph of a relation more than once, then the inverse is not a function. So all that's simply saying is this. We know that this is a function because of my vertical line test. The horizontal line test says this. If I were to draw a horizontal line through this graph and it intersects the graph in more than one place, then the inverse is not a function. Horizontal line test. The inverse is not a function. Does this relation represent a function? Does the relation itself represent a function? Yes. Why or why not? Because of the vertical line test. That tells us that it is. Does the inverse represent a function? The answer is no, because of the horizontal line test. I can draw a horizontal line that will intersect the graph in more than one place. If I were to sketch the inverse of that function, it would not be a function. In fact, let's do an example like that. Consider the graph of the relation shown. Determine whether a relation and its inverse are functions. Sketch the graph of the inverse. State the domain and range intercepts for the relation and the inverse, and state any invariant points. Okay, a lot of things to do here. Let's do it. Determine whether a relation and its inverse are functions. Is the relation a function? Yes. The original relation is a function. I can draw as many vertical lines as I wish here. It will only intersect the graph in one place. The inverse is not a function. And again, we know the inverse is not a function because of the horizontal line test. If I draw a horizontal line, it can intersect the graph in more than one place. Therefore, the inverse will not be a function. Sketch the graph of the inverse. Sketch the graph of the inverse, I simply take the points that I see on the original function and switch them around. Let's do that. And let's plot those points. I've got 0, -6. X is 0, y is -6. I've got 4, -4. I've got 4 and 0. 2 and 2. 2 and 6. Let's jot out the points in the order in which I just plotted them. Zero, -6 joins to 4, -4. It joins here, here, and here. And there is the graph of the inverse function. And you can see that the graph of the inverse and the graph of the original, I think I left out a point here. Yeah, this part of the graph shouldn't be there, I think. Yeah, this part of the graph should not actually be located here because you can see the original function only went over to here. I'm not sure what that part of the graph is doing there, so try and ignore that, please. It's just this part here, okay? This doesn't exist. And you can see that the graph and its inverse are indeed reflections of each other in the line y equals x. Now, we said that the inverse is not a function. We said because of the horizontal line test it wasn't a function. Now we can clearly see because of the vertical line test that is not a function as well. Because now that I've graphed it, I can use the vertical line test and show that it's not a function. Because a vertical line will pass the graph in more than one place. So I've graphed the function, state the domain and range, the intercepts for the relation, and the inverse relation. Let's do the domain and range. And again, remember, we're just looking at this graph right here. The domain is the values of x for which the function is defined. So I can find points on this graph between -6 and 6. And the range is the values of y that I can find points on the graph. And I can find points on the graph between 0 and 4. The new function, let's look at the domain and range of the new inverse function. The domain of the inverse, let's see here. The domain of the inverse is between 0 and 4. I can find points on the inverse graph between 0 and 4. And the range of the graph is between -6 and +6. I want you to notice something very important here as well, and that is that the domain of the original function between -6 and 6 became the range of the inverse. And the range of the original function between 0 and 4 became the domain of the inverse. And if you think about that, that makes perfectly good sense. Because, remember, we switched x and y values. The x values here became the y values here. So my domain here became my range here. And the range here became the domain here. So by switching the x and y values, we automatically switch the domain and range. So if I know the domain of the original function, I know the range of the inverse. If I know the range of the original function, I know the domain of the inverse. Very important point. It did ask to state any invariant points as well. You can see that if you look at the two graphs, there is one invariant point at 2, 2. And these invariant points occur on the line y equals x, 2, 2. Okay, let's have a look at another example here. Multiple choice question. Which represents the graph of a function and its inverse? Which represents the graph of a function and its inverse? Again, you might want to pause the recording here, try this example before I actually do it. The way we do this, of course, is let's draw the line y equals x. The line y equals x passes through there. Let's draw the line y equals x passing through here. The line y equals x passing through there. And the line y equals x passing through there. We know that a function and its inverse are reflections of each other in the line y equals x. Which of these four graphs are reflections of each other in the line y equals x? And the only one that really is B. B is a true reflection of a graph and its inverse in the line y equals x. Which mapping rule is used to sketch the graph of a function and its inverse? Which mapping rule is used to sketch the graph of a function and its inverse? We know that a function and its inverse are reflections in the line y equals x. The xy values become the yx values. There's the mapping rule right there for a function and its inverse. We switch around the x and y. That's all we need to do to create the inverse function. So the answer to that one is C. Example 5. What is the equation of the inverse that you see right here? The equation of the inverse of this function. Again, let's start with y equals 1/2 x subtract 2/3. If I want to find the equation of the inverse, I switch x and y. And I proceed to solve for y. So I solve for y. Solve for y, I simply need to multiply now both sides by 2. Don't forget to multiply everything by 2. And I get 2x plus 4 over 3 equals y. 2x plus 4 over 3 equals y. Now, obviously, if you look at the four answers there, neither one of them are written in that form, so I probably need to find a common denominator here of 3. So I get 6x over 3 plus 4 over 3 equals y. Y can be written as the inverse function after the minus 1 of x equals 6x plus 4 over 3. 6x plus 4 over 3 answers D. Remember 2 steps. Switch x and y. Solve for y. These are the 2 steps involved in finding the equation of the inverse. What is the domain of the inverse of this function? The domain of the inverse of that function. The domain of the inverse is equal to the range of the original function, isn't it? So the domain of the inverse is equal to the range of the original function. What I need to do here is I need to think about what this graph looks like, and I need to figure out the range of that function. If I know the range of this function, then I know the domain of the inverse, because we just explained that the domain of the function is equal to the range of the inverse, and vice versa. So I'm looking for the domain of the inverse, so I really need the range of the original function. So the range of this function is equal to the domain of the inverse. Let's find the range of the original function here. It's a parabola. F of x equals 3x squared plus 6x subtract 1. I know it's a parabola. It's a parabola that opens upwards. All I really need is the vertex of this parabola to be able to do this. Let's find the vertex of the parabola. You may need to recall work from level 2 to do this. X equals negative b over 2a will give me the x coordinate of the vertex. Negative b over 2a is a negative 6 over 2 times 3, which is a negative 6 over 6, which is a negative 1. That's the x coordinate of the vertex. To find the y coordinate of the vertex, which is the important one actually, I need to plug that value of x back into my function. So I'm going to find the f of negative 1. 3 times a negative 1 squared plus 6 times a negative 1, subtract 1. So we got 3 here, subtract 6, subtract 1. So negative 3 subtract 1, which is a negative 4. This is a parabola with its vertex at negative 1, negative 4. So if I'm going to do a quick sketch here, let me try and make that a little tidier here. If I want to do a quick sketch of the parabola, its vertex is at -1, -4, -1, -4, and this parabola opens upwards. There's my parabola right there. The range of this function is equal to the domain of the inverse. So the range of this function is going to be y such that y is greater than or equal to -4. So the domain of the inverse is simply going to be x such that x is greater than or equal to -4. Because it's domain, so we've got to consider the x values. X such that x is greater than or equal to -4. The answer is D. So look at another example here. I think this is the last one. What is the x-intercept for that function, for the inverse function? The x-intercept for the inverse function. Well, let's find the inverse function. Y equals -2x plus 4. I'm also thinking here the x-intercept for the inverse function. Well, now let's do it this way, just to be sure. So here's the original function. Let's switch x and y. X equals -2y plus 4. And let's solve for y. So I get x subtract 4 divided by -2 equals y. I guess we can leave it like that. The f of -1 of x equals x subtract 4 divided by -2. I'm looking for the x-intercept. To find the x-intercept, you should know that we let y equal 0. Always do that. So we let y equal 0. Y is the f of -1 of x. So I let that be 0 equals x subtract 4 over -2. Cross multiplying here, I get x subtract 4 equals 0. X is equal to 4. The x-intercept is 4. And I guess we could have done it another way here, and that's what I was thinking about earlier actually. The y-intercept of this function will become the x-intercept of the inverse function. But I wanted to be sure by actually finding the equation of the inverse function here, which I did, and then to find the x-intercept, I'll let y be 0. Cross multiply, x equals 4. Okay, that ends this particular lesson, but let's have again a quick look at the key ideas here. You can find the inverse of a relation by interchanging the x-coordinates and the y-coordinates of the graph. The graph of a function, the graph of the inverse of a relation is the graph of the relation reflected in the line y equals x. The domain and range of a relation become the range and domain, respectively, of the inverse. We use the horizontal line test to determine if an inverse will be a function. And you can create the inverse that is a function over a specified interval by restricting the domain of the function. We're actually going to do this one here more in the next section. Okay, right here. In the next lesson. Okay, that ends this lesson.